We tend to think of buildings as these immovable objects, firmly planted on solid ground.
Right.
But what if the ground itself is actually a key player in how our structures react, especially to things like earthquakes?
Exactly. And that's where this whole idea of soil structure interaction, or SSI, comes in.
Here's where it gets really interesting. We're diving into SSI today. It's this fascinating interplay between a building and the earth beneath it.
It really is. Soil structure interaction basically recognizes that a building and its foundation soil are a single dynamic system, especially when, seismic forces come into play.
Okay.
So in this deep dive, we'll unpack what SSI means for structural design, why it's so critical, particularly in earthquake-prone regions, and how modern building codes are increasingly reflecting our understanding of this interaction.
And we're drawing on some serious expertise here, right?
Yes, we'll be leaning on insights from Professor Gazetas. He's a leading figure in geotechnical engineering, and his work in soil dynamics and SSI is, well, it's incredibly valuable. Extensive research, practical applications, the whole deal.
Great. So our mission today for you listening is to cut through the complexities, get to the core of SSI. What is it, and why does it fundamentally change how we should approach structural design?
Sounds good.
So let's start by really defining what we mean by soil structure interaction. Lay it out for us.
Okay. So Professor Gazetas introduces SSI as a pretty broad field. It has specific applications to various foundation types. Think shallow footings, deep piles, retaining walls, stuff we might even touch on more in the future. And while the basic idea to, the ground affects the building isn't fundamentally new.
Right, that seems intuitive.
Exactly. But what is evolving significantly is how modern codes provide much more detailed methods to analyze and quantify these effects. The physics hasn't changed, but our ability to model and account for SSI, that's become much more refined.
So it's not a completely new concept then, but our toolkit for understanding and modeling it has just gotten way more sophisticated.
Precisely.
Now, Professor Gazetas breaks down this SSI analysis into two main categories, right? Inertial effects and kinematic effects. Let's tackle inertial effects first. What's the core idea there?
Okay, inertial effects, they describe how the dynamic behavior of the structure itself shifts because the supporting soil deforms and the foundation moves during an earthquake.
How it shakes, basically.
Yeah, exactly. This interaction directly alters the structure's fundamental period. That's its natural frequency of oscillation, how it likes to sway, and its damping, which is its ability to dissipate energy. The key takeaway is that the flexibility, the give in the soil, can change how the entire soil foundation structure system vibrates compared to, say, a building on rigid bedrock.
Got it. So that flexibility can essentially retune the building's natural sway, which could either help or hurt its performance in an earthquake, I guess.
It can go either way, absolutely.
Okay. Now, kinematic effects, they sound a bit more, indirect. What's the main principle behind those?
Right. Kinematic effects deal with how the earthquake ground motion that actually reaches the base of the structure is different from the free field motion.
The free field being?
That's what the ground would experience if the building wasn't even there. So as seismic waves travel upwards, they interact with the foundation, which is often stiffer than the surrounding soil, you see.
Okay.
And this interaction modifies the motion that the structure actually feels at its base. Professor Gazetas used a great visual for this, contrasting the undisturbed ground shaking, that free field motion we use for the design spectrum, with how those waves are altered when they hit the foundation and the building. You end up with a different foundation input motion.
Okay, so the building isn't just passively reacting to the earthquake. Its sheer presence actually changes the shaking right at its own feet.
Exactly right. And importantly, this is a two-way street. The structure's response, its swaying and shaking, generates forces. Think overturning moments, shear forces. And those get transmitted back down into the foundation and into the soil. It's this continuous feedback loop. Structure, foundation, soil, back again. That's soil structure interaction.
Let's dig a bit deeper into those kinematic effects then. For buildings with foundations at or just below the surface, you said the motion at the foundation can deviate from the free field. How does that happen?
Well, when seismic waves hit a surface or a shallow foundation, the difference in stiffness, the foundation versus the soil, can cause certain frequencies of the wave to be filtered or maybe amplified.
Like hitting an obstacle?
Sort of, yeah. Imagine waves hitting something solid, they'll diffract, reflect. The foundation's presence and its shape influence those incoming seismic waves. And interestingly, Professor Gazettis pointed out that these kinematic effects can sometimes lead to a reduction in the effective seismic forces the structure experiences.
Wow, okay. That's counterintuitive, isn't it? The interaction can sometimes shield the building a bit.
Precisely. It
Yeah.
can happen. However, for deeply embedded foundations, especially piles, kinematic effects introduce a whole different kind of loading.
Oh.
Yeah, as the seismic waves propagate up through the different soil layers, they push and pull directly on the piles themselves. This causes bending moments and shear forces in the piles, even before the structure above really starts to sway and generate those inertial forces we talked about.
Oh, I see.
So for deep foundations, you have to account for both: the kinematic loading from the ground movement and the inertial loading from the building's response. Two separate things happening.
That makes the distinction between shallow and deep foundations really clear regarding kinematic effects. Okay, now thinking about SSI effects overall, particularly the inertial ones, when are they critical enough that we absolutely need to consider them in design?
Professor Gazettis highlights several key situations. First, if the soil's flexibility significantly increases the structure's fundamental period.
Lengthens the sway time.
Right. And if that elongated period moves the building's natural sway closer to the dominant shaking frequencies of the earthquake, well, that can lead to resonance. Much higher forces. Big problem.
Okay, resonance is bad. Got it.
Second, SSI often leads to larger overall displacements of the building. It just moves more. So if your structure is located close to neighboring buildings, accurately predicting these larger movements is crucial. You need to avoid collisions, right? Pounding.
Definitely scenarios where ignoring SSI could be serious. Are there other indicators? Like, what about the soil itself?
Absolutely. The stiffness of the soil is a major factor. Very soft soils, you can generally characterize them by a low average shear wave velocity within the pressure bulb under the foundation.
Pressure bulb.
Yeah, roughly think of the zone of influence, maybe 3 times the foundations with deep. Soft soils in that zone mean more significant SSI effects.
Okay.
And lastly, for very tall, slender structures, towers, for instance, geometric nonlinearity, what we call P-delta effects.
Where the load itself amplifies the sideways movement.
Exactly, where the axial loads, P, amplify the effects of lateral displacements, delta. These P-delta effects can become really significant, and they're directly influenced by how much the foundation moves and rotates, which is, of course, tied right back to SSI.
Right, so soft ground, tall, slender buildings. Those seem like prime candidates for these inertial interactions. Now let's switch back to kinematic modification. You mentioned Professor Gazettis emphasized the word should in the code. He said it carries significant weight.
Yes, that was a really crucial clarification he made. In European codes, apparently should isn't just a mild suggestion. It implies a strong recommendation. You're expected to follow it unless you have a very compelling, technically justified reason not to.
So not optional, really.
Pretty much. Deviating often requires specific justification, maybe even regulatory approval at a national level. Professor Gazzetta stresses that ignoring kinematic modification when the code says you should consider it can often lead to an unconservative design. You might underestimate the demands, although, as we said, sometimes it can reduce the calculated forces too.
Right, the shielding effect. So in what situations is considering kinematic modification particularly important then?
Well, as we touched on, it's vital for deep foundations, piles, caissons, that sort of thing. Also, for what are called banded foundations. Think basements, essentially at least 2 stories deep, or an equivalent depth where the vertical walls are in full contact with the surrounding soil. That embedment itself significantly alters the incoming seismic waves.
Makes sense. The deeper it is, the more interaction.
Exactly. Bridges are another key area, especially those with large abutments or what they call integral bridges, where the deck and supports are connected without joints. And also for very large foundations. If you have a mat foundation that's, say, over 50 meters in length or width.
Huge.
Yeah, really big.
Yeah.
In that case, the seismic waves don't arise at all points underneath simultaneously. This non-uniform arrival can lead to complex interactions, even some cancellation effects across the foundation's footprint.
That image of a massive foundation feeling different parts of the earthquake wave at slightly different times, that really clicks.
Oh, it does, doesn't it? The code also mentions you might be able to neglect kinematic modification for very flexible piles based on a ratio of the soil stiffness to the pile stiffness related to its active length. But that's getting a bit specific.
Okay.
And a final important point he made. Kinematic interaction is not considered for the vertical component of ground motion, only horizontal.
Interesting detail. So it's primarily about how the side-to-side shaking is modified at the foundation. Which leads me to the next question. How do we actually model these complex interactions in our analysis? It sounds like it could get incredibly complicated.
It certainly can be. Professor Gazettis notes that a full-blown finite element model, modeling the entire soil volume, the foundation, the structure, they can be computationally very intensive, very demanding on computers.
Like that.
So building codes permit a more practical approach. We can represent the soil's behavior using a system of springs and dashpots attached to the foundation.
Ah, springs and dashpots. The engineer's friends.
Pretty much. These springs capture the stiffness of the soil in all 6 degrees of freedom, moving side to side, up and down, back and forth, and rotating around each of those axes. The dashpots represent the soil's damping properties, its energy dissipation.
Okay, so replacing the continuous soil with discrete elements at the foundation. Are there any specific tricks or considerations when using them for SSI?
Yes, definitely. For pile foundations and other deeply embedded structures, the code emphasizes the importance of coupling the horizontal and rotational springs.
Coupling, meaning?
Meaning that a horizontal push on the foundation doesn't just meet horizontal resistance, it also generates a rotational resistance from the soil, and vice versa. A twist can induce a sideways force. This coupling is generally less significant for shallow foundations, but critical for deeper ones.
Okay.
And for initial assessments, or just to get a handle on things, engineers can use elasticity-based formulas to estimate the stiffness of these springs for different foundation shapes and soil profiles. These formulas exist.
So we're essentially replacing the dirt with springs and shock absorbers. Where do we actually find the values for the stiffness and damping of these things? Are they just rules of thumb?
No, much better than that now. Annex D of the code provides detailed equations and guidance for calculating these stiffness and damping coefficients for foundations, covering various modes of vibration. And importantly, these aren't just empirical correlations. They're derived from extensive finite element analyses and analytical solutions.
So based on solid calculations?
Yes, but simplified into practical expressions for design. Professor Gazettis highlighted this as a significant advancement. It makes dynamic analysis more accessible, more rigorous, without needing, super complex soil models for every case. He mentioned something about avoiding wingless springs, suggesting simpler models are now better supported.
That sounds like a really valuable resource for engineers doing this work. How is the damping part, the energy loss, accounted for in this spring dashpot model?
For the translational modes, the sliding and vertical movements, the damping coefficient for the dashpot is related to things like the soil's density, the shear wave velocity, how fast waves travel through it, and the area of the foundation. Rotational damping is a bit more complex and tends to vary with the frequency of the earthquake shaking.
Ah, frequency dependence.
Oh.
Okay, so earthquake shaking isn't just one frequency, it's a whole mix. How do we handle the fact that stiffness and damping might change depending on the frequency of shaking?
That is a key challenge in SSI. In reality, soil stiffness does change with frequency. The code offers a simplification here. It generally allows you to use frequency-independent stiffness values for the springs.
A single value.
Yeah, ideally chosen based on the dominant frequency of the combined soil structure system, or sometimes even just the static stiffness for simpler analyses. It's a necessary approximation to make the analysis practical for most projects.
Makes sense. You have to draw the line somewhere. Now, we know soil isn't perfectly elastic, right? Especially during strong earthquakes, it deforms. It doesn't just spring back perfectly. How does the code address this nonlinear behavior?
Good point. The code permits what's called equivalent linear analysis.
Equivalent linear.
Yeah. In this method, you adjust the soil's stiffness, represented by its shear modulus, G, based on the expected level of deformation or shear strain in the free field. You'd typically estimate these strain levels from a separate, simpler analysis, like a one-dimensional site response analysis.
So if you expect bigger shaking, bigger strains.
You use a softer, reduced stiffness for the soil in your SSI model. It's basically a way to approximate the soil's actual nonlinear strain softening behavior in a linearized framework. It's a common simplification.
Okay. And what about the energy that radiates away from the foundation? Waves spreading out into the ground, that's radiation damping, isn't it?
Correct. That's a major way energy gets dissipated in SSI. The damping formulas provided in the code, particularly for this radiation damping, are generally applicable when the frequencies you're interested in, like the building's natural frequencies, are higher than the natural frequency of the soil deposit itself.
The soil has a natural frequency.
Oh, yes. If the soil layer has its own resonant frequency, and your building is shaking slower than that, the radiation damping can actually become significantly smaller. This is especially true for layered soils, not just a theoretical uniform half space extending infinitely downwards.
So using those standard formulas might overestimate how much energy is dissipated through radiation in certain real-world soil profiles.
Exactly. Factors like distinct soil layers, or soil that gets stiffer with depth, or the presence of bedrock at a relatively shallow depth, all these things can significantly reduce radiation damping compared to the predictions from those simplified uniform soil models. Something to be careful about.
Now, the webinar also talked about a displacement-based approach and how it accounts for nonlinearity. What's the core idea there?
Right, the displacement-based approach often involves nonlinear static analysis, something called pushover analysis. It directly aims to capture the significant nonlinear force versus deformation behavior of the soil foundation system.
Pushing the building sideways computationally.
This essentially, yes.
Okay.
And the idea is that this soil nonlinearity can sometimes be even more influential than the frequency dependence of the springs we just discussed. This approach allows for using nonlinear springs directly in the model springs, whose stiffness changes as they deform.
More realistic then.
Potentially, yes. And more advanced methods might even use nonlinear finite element or finite difference analyses just for the foundation part to derive its low displacement characteristics in detail. That gives a very sophisticated representation of the soil behavior.
And Professor Gazelles highlighted something about foundation uplift and sliding being treated differently now. Why is that important?
Yes, this is a really key shift in thinking, actually. Older codes often implicitly discouraged, allowing any foundation uplift where one edge lifts off the ground or any sliding at the base. The requirements were often very conservative.
You had to keep it fully pinned down.
Pretty much.
Yeah.
But research, including work by Gazettas and others, has shown that allowing some controlled uplift on the tension side and some limited sliding during really strong shaking can actually be beneficial.
Beneficial? How?
It acts like a natural fuse. It can help dissipate energy and can actually reduce the overall forces transmitted up into the structure. The new code explicitly permits considering these nonlinear foundation behaviors, uplift and sliding in the analysis. It's a much more realistic view of how foundations can perform and sometimes fail gracefully during intense earthquakes.
Wow, that's a major change in perspective. Sometimes letting things move a bit at the base can actually be safer for the building overall.
It can be, yes, if designed properly to accommodate it.
Okay, so how is SSI handled in more complex time history analyses, where we use actual recorded earthquake motions as input?
You can still use the spring and dashpot approach in time history analysis. More sophisticated setups might even incorporate frequency-dependent stiffness for those springs, trying to capture that behavior more accurately. Radiation damping is typically added to the inherent material damping within the soil model itself. Annex D, again, provides guidance on selecting appropriate spring and dashpot properties for these dynamic analyses.
We talked about the limitations of those radiation damping formulas earlier. Can you just quickly reiterate the main takeaway there?
Sure. The main point is simply that formulas based on that idealized assumption, a uniform infinite soil deposit, tend to overestimate radiation damping in many real-world sites. If you have layers or rock nearby underground, those conditions can significantly reduce how much energy actually radiates away. Need to be cautious.
Got it. Consider the actual subsurface conditions. Don't just rely on the simplest model. Now let's quickly revisit kinematic effects. How are those modeled in the more advanced analyses?
Professor Gazette has explained that kinematic effects can be integrated right into the analysis in a single step, combined directly with the inertial effects, especially within those more complex models like finite element.
Okay.
Finite element models are becoming more common for this kind of comprehensive approach. For pile foundations specifically, a common technique is called Winkler modeling.
Winkler.
Yeah. You basically discretize the soil into horizontal layers, and the pile is connected to the free field ground motion, which you'd get from a separate 1D site response analysis via a series of springs and dashpots all along its length.
Like springs connecting the pile to the moving soil at different depths.
Exactly. Finite element analysis also allows for applying the earthquake motion directly at the base of the whole soil model, provided you use appropriate boundary conditions at the edges to simulate waves propagating outwards, not reflecting back unrealistically.
And for piles, are there simpler ways to estimate these kinematic effects, maybe without needing those complex models?
Yes, Winkler modeling itself is already a simplification compared to full 3D FEA. The webinar mentioned other simplified methods exist too. A very basic approach, maybe for preliminary design, is just to calculate the maximum bending moments induced in the piles purely by the free field soil movement, and then apply those as static loads in the structural design.
Conservative, but straightforward.
Right. It gives you an estimate of those kinematic demands.
And when we have both kinematic forces bending the piles from the ground motion and inertial forces coming down from the swaying structure, how do we combine them to get the total effect on, say, the pile?
Good question. The simplest, most conservative method is just direct addition. Add the bending moments from kinematics to the moments from inertia. If you can show that the dominant frequencies controlling the inertial response, the structure swaying, and the kinematic response, the ground shaking, are significantly different, a less conservative approach is allowed, using the square root of the sum of the squares, the SRSS method.
SRSS, yeah.
But ideally, the most accurate way is a fully coupled analysis that considers both effects happening simultaneously, modeling the seismic wave transmission and the interaction dynamically.
Now, there was that really important point again about the word should in the code. You stressed it, Professor Gazzetta stressed it. It's not just a suggestion.
Absolutely worth repeating. As he clarified, particularly in the context of European codes, should signifies a strong recommendation. It carries real weight. Deviating usually needs proper technical justification and might require national regulatory approval. It underscores that things like kinematic interaction aren't meant to be ignored lightly when the code uses that term.
Okay, message received on should. There were also some specific audience questions covered in the webinar. Let's touch on those quickly. One was about ensuring the foundation is stiff enough to transmit loads uniformly. What's the guidance there?
Yeah, that concept of sufficient stiffness is largely qualitative. It really relies on engineering judgment. The foundation just needs to be rigid enough to distribute the loads reasonably evenly to the soil without bending excessively itself. There isn't a hard numerical threshold given in that part of the code.
So, judgment call. What about the torsional stiffness of piles? Should engineers routinely worry about piles twisting?
Yes, it should be considered, especially if you have pile groups or if the building itself is asymmetric, making it potentially susceptible to torsional vibrations during an earthquake. It's not always the most critical factor, but it needs to be on the checklist.
And P-delta effects in relation to SSI. Is there a specific trigger point mentioned in the code for when those become significant?
The threshold for when P-delta effects need explicit consideration isn't defined right within the SSI section itself. It's usually referenced in other parts of the structural code, like Eurocode 8 Part 5, dealing with overall stability and interstory drift limits. There are specific values, like a theta coefficient threshold, which might differ for buildings versus bridges, for example.
Okay, so it's linked but defined elsewhere. What about how piles connect to the structure above? Pile head fixity, pinned, fixed, embedded. Does the code dictate how to model that?
The code basically acknowledges that modeling that connection, the degree of fixity, depends heavily on the actual construction details. It requires the engineer to use their professional judgment based on the specific situation. The code doesn't, and probably can't, eliminate that responsibility.
Right, details matter. Finally, there was that mention of a 100-meter guideline for using nearby soil data if site-specific data is limited. What's the thinking behind that number?
The 100-meter guideline, particularly when soil variability is expected to be limited, is really intended as a practical boundary. It's to discourage engineers from, say, extrapolating soil conditions from a borehole that's maybe a kilometer away.
Okay, prevents over-extrapolation.
Exactly. It encourages getting site-specific investigations done. However, it is just a guideline. It shouldn't override sound engineering judgment. If you're in an area known for very complex or rapidly changing geology, even 100 meters might be too far. Judgment is still key.
That clarifies those specific points really nicely. So as we wrap up this deep dive into soil structure interaction, what are the most important takeaways you think our listeners should walk away with?
I think the crucial points are: 1, soil structure interaction is absolutely vital in seismic design. It's not an optional extra in many cases. 2, it encompasses both how the ground affects the building shaking and how the building modifies the ground motion at its base, those inertial and kinematic effects. 3, modern codes are giving us increasingly sophisticated tools to analyze these effects, considering soil properties, foundation types, and that important non-linear behavior of soil. And finally, a thorough understanding of SSI is really essential for designing earthquake-resistant structures that can perform safely.
And it really drives home that point, doesn't it? We can't just analyze a building in isolation. We have to consider it as part of this bigger interactive system with the ground it sits on.
Precisely. The specific characteristics of the site, the soil profile, and the careful selection of the right analysis techniques, those are paramount for accurately capturing the complexities of SSI.
Definitely food for thought. So, looking ahead, one has to wonder, doesn't one? With advancements in real-time monitoring of soil behavior during actual earthquakes, plus the growing power of AI to analyze really complex data sets, how might we further refine our understanding and application of soil structure interaction in the future? Could we perhaps move towards designs that are even more resilient, maybe going beyond what our current codes even envision?
It's a fascinating prospect.
It's certainly an area with a lot of potential for future innovation. Thanks for joining us for this deep dive.